None of the podcasting programs were downloaded on any of my computers, so here we are. Okay, first question asks or states that methane gas reacts with chlorine gas to form dichromate methane and hydrogen chloride, as represented by the equation above, which is CH4 plus 2Cl yields to CH2Cl2 plus 2HCl. We're given that 25 grams sample of methane gas is placed in a reaction vessel containing 2.58 moles of chlorine. So the first part asks us to identify the limiting reactant when methane and chlorine gases are combined, and to justify our calculation with justify our answer with a calculation. So we use limiting reactant stoichiometry, and I did it for both of the products to justify and verify my answer. So I started with 25 grams of CH4 and divided it by its molar mass, which is 16.05 grams, to convert it to moles. And to convert it to CH2Cl2, we use its molar ratio, which is 1:1, as seen here. And we get 1.56 moles of CH2Cl2. Then we have 2.58 moles of Cl2, and we would use its molar ratio to convert it to CH2Cl2, which is just 1:2 from Dawn's equation. We get 1.29 moles of CH2Cl2. Obviously 1.29 is smaller than 1.56, so therefore chlorine would be the limiting reactant because it would be used up first. To confirm this, I also did it with HCl, so I got 25 grams of CH4, which was given to us, and divided by its molar mass, 16.05 grams, and multiplied it by its molar ratio of 2:2 to get 3.12 moles of HCl. I also did the same with the given 2.58 moles of chlorine times its molar ratio, which is 2:2, and that equals to 2.58 moles of HCl. So that is obviously smaller than 3.12 moles of HCl, so therefore Cl would be our limiting reactant. The next part asks us to find the total number of moles of CH2Cl2 in the container after the limiting reactant has been totally consumed. So as we determined in the last part, that chlorine was our limiting reactant, and we were given 2.58 moles of chlorine to begin with. So we multiply that by its molar ratio, which is 1:2, seen in the balanced equation, and that gets us 1.29 moles of CH2Cl2. The next question states iron reacts with oxygen to produce iron 3 oxide, as represented by the equation above, which is 2Fe plus 3/2 oxygen, which is O2, yield to Fe2O3. We're given that 75 grams sample of iron is mixed with 11.5 liters of O2 at 2.66 atm and 295 kelvins. The first part asks us to calculate the number of moles of each of the following before the reaction begins. So we need to find the moles of iron and oxygen. So to begin with, iron, we were given 75 grams of it, as stated here. So to convert that to moles, we would divide it by its molar mass, which is 55.85 grams. And we get 1.34 moles of iron. Moving on to oxygen, we would use PV equals nRT because it is a gas, so we would use the ideal gas law. Since we're given PV and T and we're not the pressure, volume, and temperature are constant, we would use the ideal gas law. And we're given 2.66 atmospheric pressure, 11.5 liters, and 295 kelvins, which is already at standard temperature and pressure, so we would not have to convert any of that. And we would just plug that into PV equals nRT to get 2.66 atmospheric pressures times 11.5 liters equals N, which is the number of moles, times constant, which is 0.0821 liter atmospheric pressures over moles Kelvin times 298 kelvins. And using algebra to isolate N, we have 2.66 times 11.5 over 0.0821 times 298, and we get 1.25 moles of oxygen. Good. Part B asks us to identify the limiting reactant when the mixture is heated to produce Fe2O3 and to support our answer with calculations. So in a previous problem, we determined the amount of moles of each species, which is 1.3 moles of iron and 1.25 moles of oxygen. So we used both of those to do a limiting reactant stoichiometry. So we start off with 1.34 moles of iron and multiply it by its molar ratio, which is 1 to 2, as seen in the balanced equation. And we would multiply it by its molar mass of Fe2O3 and divide it by a mole. So we get 107 grams of Fe2O3. Then we're gonna convert 1.25 moles of oxygen to Fe2O3, and we can do that by also multiplying by its molar ratio, which is 1 to 1.5, because 3/2 equals 1.5. And then we again multiply by Fe2O3's molar mass, 159.7, and divided by a mole, to get 133 grams of Fe2O3. So the smaller number is 107 grams of Fe2O3, so therefore iron is our limiting reactant because it gets used up first. Part C asks us to calculate the number of moles of Fe2O3 produced in the reaction proceeds to completion. So as determined in Part A, we have 1.34 moles of iron, and it is our limiting reactant that we determined from the previous problem. So we have 1.34 moles of iron times molar ratio of 1 to 2 for Fe2O3 to iron. So we divide 1.34 by 2, and we get 0.670 moles of Fe2O3. And make sure that this is 3 sig figs because we started out with 3 sig figs. That is it.